Hello everyone and welcome to this video in which we will be talking about the lateral earth pressure on flexible retaining walls and how to design flexible retaining walls. Sheet piles, we will talk about two different types of sheet piles, cantilever sheet piles and anchored sheet piles. So here in this session or in this tutorial we have two problems. One problem which talks about cantilever type and one problem which talks about the anchored type. And in this video I will cover the first problem, and let's start with a quick introduction for the cantilever sheet pile and what's the meaning and the definition of this type of retaining walls. So a cantilever sheet piles, it means that it's not anchored, and the term flexible means that it doesn't have a very thick cross section. Actually it's not made of concrete, or it's not made of reinforced concrete, it's made of steel. In most cases it's made up of steel, corrugated steel actually. It's flexible because it has a little thickness when compared with gravity retaining walls or even cantilever reinforced concrete retaining walls, the ones we have discussed before in the last weeks. And in this type of flexible retaining walls, you don't have to check sliding, you don't have to check overturning or whatever. So the typical geotechnical designs that we made last week, you don't need to satisfy these requirements here. And actually this flexible retaining wall, it acts as a best solution in weak soils, because if you have a very weak soil and you cannot satisfy the sliding, the overturning or the stresses criteria, you can use this type of retaining walls, which is called flexible retaining walls or sheet piles. So cantilever sheet pile, actually when we have our depth of excavation, typically when it's less than or equal 5 meters, you can use this type of sheet piles, which is called cantilever retaining walls. And it's called cantilever because the statical system looks like a cantilever. It's fixed here in the ground, and you have a free length which should be equal to your h plus the excavation depth, or sorry, the penetration or the embedment depth below the dredge line. You have here what's called the penetration depth, and actually this penetration depth or embedment depth is very important, and that's what provides you with enough resistance, with enough passive resistance here on the left hand side. So that's cantilever sheet pile. Under loading, when you have done your excavation and there is some live load on the top surface, this will be your let's say deformed shape. The sheet pile will rotate around a point here, which is called point of rotation, and this will be your deformed shape. So here, as you see, this part of the flexible sheet pile, it moves away from the soil on your hand, on your right hand side. So here I have active earth pressures acting on my retaining wall. However, on the left hand side, as you see here, the wall is moving towards the left. So here I have passive earth pressures acting on the retaining wall. Below the point of rotation, if I draw a horizontal line, this line here, if I draw a horizontal line passing through the point of rotation, you will find that this part of your wall, it looks like it's rotating anti-clockwise, so it's moving to the right. It's moving and pushing the soil on your right hand side. So this means that in terms of active and passive earth pressure, the pressure here below this the horizontal line should be passive, and on the other hand side, on the left hand side, should be active. This should be your earth pressures acting on your flexible retaining wall sheet pile. So if you see here, this is my horizontal line passing through the rotation point O according to the deformed line. Above this assumed line, above this drawn line, on the right you have active earth pressures, on the left you should have passive earth pressures. Below this line, on the right you will have passive earth pressures, and on the left you will have active earth pressures. This will be the final earth pressure acting on your retaining wall. As you see here, this is my point of rotation here. I will put a point. So my point of rotation is here. This is my point O. And as you see here, above the point of rotation, on the right hand side active pressures, on the left passive pressures. Below this point of rotation, I have passive to the right and active to the left. However, for design purposes, it might be much easier to neglect what's lying beneath my point of rotation. How can we do this? You can do this by assuming that these stresses here, you can replace these stresses by just one force, which is called R, as if it's a resultant force passing through this point, which should be very close to the point of rotation O. So here, this is for design purposes. We will assume that whatever lying below the point of rotation will be neglected, and that's by replacing all the stresses below the point of rotation by just one force, which is a resultant force passing through the bottom of your flexible retaining wall. So here, in this case, for design purposes, we will deal with the problem like we have done before. On your right hand side, you will have active earth pressures. On the left hand side, you will have passive earth pressures. So all we have to do is to draw the active earth pressures from the right, to draw the passive earth pressures from the left, and our design outcome, or our design output, our design output should be your D, your penetration or embedment depth. You will be given your H, the depth of excavation. That's your problem. You have your excavation depth is given, and then you will be required to calculate the penetration depth. Maybe in another complicated problem, you will be given the penetration depth D, and you will be required to get the maximum height of excavation that can be done in the field. So whatever, you will have only one unknown, and as I told you here, the resistance in this type of sheet piles comes entirely from your passive resistors. So it's very important to get your penetration depth or embedment depth accurately. And we take a factor of safety in this estimated value, as you will see in the design. Let's start with problem number 1. So in this problem, I have a flexible sheet pile, cantilever type. The excavation depth is 5 meters and the penetration depth is unknown, it's D. I have a life load which is 10 kilonewton per meter square. It's typically the life load of traffic. I have 2 soil layers and I have a groundwater table. It should be at the same elevation on the right hand side and on the left hand side. So I have here groundwater table is here and here. On both sides we have the groundwater table at this level. What about our soil layers? We have 2 sandy soil layers. For the first soil layer I have the unit weight 18 and friction angle of 30. And for the second soil layer I have a unit weight of 20 and a friction angle of 35 degrees. So according to the definition I told you about in the last slide, we will draw active earth pressures on the right side, on the right hand side, to the right of your pile, of your sheet pile, sorry. And we will draw passive earth pressures to the left of my sheet pile. To do this, I need to use Rankine theory. I will use Rankine theory assuming that my sheet pile is frictionless. And if the sheet pile is steel, actually this assumption is good because steel doesn't have much friction with soil like concrete. So here I will use Rankine theory by assuming that the sheet pile is frictionless. And let's get our K active and our K passive. We don't have any inclined backfill, so this is a very normal case. For K active it's 1 minus sine phi over 1 plus sine phi. For the first soil layer, which has a friction angle of 30 degrees, I will get a K active of 1/3. For the second soil layer, which has a friction angle of 35 degrees, I will get a K active of 0.271 and a K passive of 3.69. During the design, I will take only 1/2 of my passive resistance as a factor of safety. So we will see this in the next slide. Let's put here our K active, and that's for the second layer, and our K passive. Let's now get our active earth pressures and our passive earth pressures. So as I told you in the tutorial of earth pressures using Rankine theory, the locations where you have to get your earth pressure should be as following. First point, you have to get your earth pressure at the top, so I will call this point number 1. Then if you have a line separating between 2 different soil layers, please get your stress 2 times, 1 time just above this line and 1 time just below this line. So these my points 2 and 3. Then if you have a groundwater table, I will get my stress here at the groundwater table, and even in the case of absence of groundwater table, it may be I want to say like it may be more safe to get your stress at the dredge level, this level here, on both sides, on the active and on the passive. So get a stress at this point number 4, and at the bottom of your retaining wall, this is point number 5. These are your locations: top of your sheet pile, bottom of your sheet pile. If you have a separating line between two different soil layers, one point above and one point beneath, and if you have a groundwater table, put a point at the location of your groundwater table. And finally, it may be better in some problems to get the earth pressure at the dredge level. On the passive side, this is my top point here. This is point number 6. And at the bottom here, this is my point number 7. Let's see our active earth pressures. I don't have any C here. I don't have clay. I don't have C strength parameter. So my earth pressure in the active side will be gamma H plus life load times K active. And on the passive side, it will be gamma H times K passive because I don't have a life load. But I will take only 0.5 of the resistance. 50% of the resistance only will be taken on the passive hand side, mainly because of two reasons. The first reason is that you are not sure that the passive resistance will be developed completely, because in order to develop the passive resistance, the sheet pile has to move to the left a large distance, and this may not happen in reality. The second reason is just taking a factor of safety, because this is your resistance and it's good to take a factor of safety in your resistance. So let's start our calculations. At point number 1, the term gamma H is equal to 0 because you are at the surface. The life load is equal to 10. K active of the first soil layer is 1/3. That's 3.33 kilonewton per meter square. For the second point, this point here, your effective vertical stress gamma H is 18, the unit weight, times 1.5 your height. 18 times 1.5. Your life load is 10. And again, point 2 lies inside soil number 1. So it will take K active 1. So that's 1/3. And this will be equal to 12.33 kilonewton per meter square. For point number 3, if you remember from the tutorial on lateral earth pressures, I told you that if you are at the same elevation, because point 3 and point 2, they are just at the same position, then this term, which is gamma H plus life load, will be the same. You see, for point 3, it's the same gamma H and it's the same life load. However, what's different here is your K active, because your point number 3, now it's inside soil number 2, and it has a K active of 0.27. So I put here 0.27. That's 9.99. So you see here, I have at a depth of 1.5 meters, I have a drop in the earth pressure. The earth pressure drops from 12.33 to 9.99. Then at point number 4, your effective vertical stress is 18 times 1.5 plus 20 times 3.5. So that's here your effective vertical stress due to the own weight of soil. What about your life load? It's 10. And at point number 4, My K active is 0.27, so my K active is 0.27. That's 28.89 kilonewton per meter square. Then for point number 5, at the bottom of your sheet pile, the effective vertical stress should be 18 times 1.5 plus 20 times 3.5 plus 10, because here below the groundwater table I will just take the submerged unit weight. It's 20 minus gamma water, and I assumed here that my unit weight of water is 10. So my submerged unit weight is 10. 20 minus 10 is 10 times D, which is unknown. So you see here, this part is the effective vertical stress due to the own weight of soil. I have here 10 times D. Then I have my life load portion is here plus 10. And my K active for the soil layer, for the second soil layer, is 0.27. So the final shape of the active earth pressure at point 5, I call this, by the way, EA, E active. So I have E1 to E4, and at point 5, I call that EA. So that's 28.89 plus 2.7 D. And that's all about the active earth pressure. Let's now look into the passive earth pressure. So at point number 6, I don't have a surcharge, I don't have any own weight of soil, so it just at point 7, this should be E passive. I will correct it for you. So the E passive, it's 10D. That's the earth pressure at point 7. At point 6, the earth pressure is 0. At point 7, the earth pressure should be as follows. Gamma H is 10, which is 20 minus gamma water, because I am below the groundwater table. So it's 10 times D. So that's my vertical stresses due to the own weight of soil. Times K passive. K passive is 3.69. And I will take 50% of the passive resistance. That's 18.45 D. So taking only 50% of the passive resistance will give you 18.45 D. Sometimes you may just, while calculating or estimating the value of K passive, take 50% of the K passive value. So if it's 3.69, you can take 50% of the K passive value. But I think it may be better to get your K passive first, 1 over K active, without taking any reduction, and then do the 50% reduction in the earth pressures equation. So if you get your passive earth pressure, put 50% in front of your equation, and here put your equation, which is gamma H K passive, and if you have a C value, you will add it here, 2C square root of K passive. So it may be because here if you have a C5 soil, you shouldn't apply the reduction to the K passive only. You should apply the reduction to the stress, to the whole stress equation. So here in my problem, I took K passive is 3.69, as you see here, but I applied the 50% reduction to the whole equation of earth pressure. If we plot the earth pressures on our drawing, look here please. The earth pressure at point 1 is 3.33, at point 2 is 12.33, but it drops to 9.99 at the same depth. Then it increases to 28.89. Then it increases to 28.89 plus 2.7 D. How did I know that the slope of this line is not the same as the slope of this line? Because of the existence of my groundwater table. If I have a groundwater table, I will have two broken lines as you see here, two different lines with two different slopes. If I don't have a groundwater table here and it's the same soil layer with the same properties, then it will be just one line with the same slope. On the left side, I have E passive of 18.45 D. So as I told you here, that's your E passive. It's not E active. I corrected it here. Right now, after drawing your earth pressures, let's get our forces. You must get your moments around this point here at the bottom of your cantilever retaining wall. You don't have a choice. Why must I get my moments here? Because if you remember, according to the definition and the introduction I told you in the first slide, we have neglected some stresses here. We have neglected some stresses here when I told you that I have passive here and active here below the rotation point. Do you remember? So we have neglected some stresses below the rotation point and put instead a resultant force which is called R. I don't know how much should be this resultant force. So if you don't want to bother yourself with the quantity of this resultant force, you have to get your moment around this point. So you will apply equilibrium equation sigma moment at the base is equal to 0. And since the resultant force is passing through the base, it will be cancelled in the equilibrium equation. So you don't have a choice. You must get your moments around the base of the flexible retaining wall and equate it to 0. So to get the moments here at the base, let's get our forces and the arm of each force. So this is a repeated process that we have gone through before. I will divide this trapezoid into a rectangle and a triangle. Then this trapezoid will be divided into a rectangle and a triangle. And this trapezoid will be divided into a rectangle and a triangle. This triangle will give you F7, which is for the passive resistance. Getting the area of any rectangle, you have 3 rectangles and 4 triangles here. Getting the area of each rectangle and each triangle will give you the force value for 1 unit length of your sheet pile, 1 meter length of your sheet pile in the perpendicular direction, in the direction perpendicular to the screen. So let's see some examples here. Let's see F1 F4 and F7, for example. So F1, it's the area of this rectangle here. So the area of this rectangle should be 3.33 times 1.5. And that's 5 kilonewton per meter run. How much is your arm? The arm is your D, the penetration depth, plus 3.5 plus 1.5 over 2. So my arm is D plus 3.5 plus 1.5 over 2, because this force is at the center of my rectangle. What about F2? No, sorry, I will take F4. So I'm picking some examples from the forces. Let's take F4. So F4 should be the area of this triangle. This point is 28.89, the ordinate is 28.89, and this point, the top point of my triangle, is 9.99. So the base, this base, is equal to 28.89 minus 9.99. So my F4 should be 0.5 times the base times the height. My base is 28.89 minus 9.99 times the height, which is 3.5. What's the arm of this force? It will be your penetration depth plus 1/3 of the height of the triangle, which is 3.5 over 3. For F7, F7 is the area of a triangle, so it's 0.5 times your base, which is 18.45 D, times the height, which is D. And I will assume that any force in this direction will take a positive sign, any force in this direction will take a negative sign, so F7 will take a negative sign. The arm for F7 is D over 3, 1/3 of the penetration depth. You see here that F7 will be equal to negative 9.225 D squared. You will do the same for the rest of forces. Get the force by taking the area of each rectangle and each triangle and get your arm. Getting your forces and putting them here in your table. And as you see here, I have a negative sign before my F7 value, because it acts as a resistance force in an opposite direction. And you don't need to get the summation of your forces in this cantilever type of problems. You don't have to get the summation of your forces, unless, of course, you are required in the problem to get the summation. But if you are after the penetration depth, you don't need to get your summation of forces. Now, I have shown you how to get the arm of F1, F4, and F7 as a final example. Let's look what about F4. Sorry, we have taken F4 before. Let's take F2. So the arm of F2 should be D plus 3.5 plus 1/3 of 1.5, and that's the arm of F2. D plus 3.5 plus 1.5 over 3. So get your arms, put them in your table, and then get your moment. So the moment will be your force times the arm. A force times the arm will give you the moment due to each force. For moments, I usually assume that any moment acting anti-clockwise will take a positive sign. Any moment acting clockwise will take a negative sign. So as you see here, the moments due to the active forces will take a positive sign. So from F1 to F6, all your moments have a positive sign. And you see here that you have for F6 and for F5, the moment will be unknown in d square, and for F6 it will be unknown in d cube. For F7, the moment will be negative because it's acting clockwise, and here you need to get the summation of the moments you have. So I will get the summation of all these moments and put it here in my table. Now you see here that I have one unknown, which is d, and that's your penetration depth that you want to get. And my equilibrium equation is sigma moment at the base should be equal to 0. So put your summation of moments here and equate it with 0. Here this is a problem which is unknown only in one unknown. It's unknown only in d. So put this problem in your calculator and solve for d. And while solving for d, put a reasonable value to start trying with. So put penetration depths, for example, 3 meter, 4 meter, and your calculator will give you the answer for this equation. So my d value is 9.38 meters, and we have to take another factor of safety. I know that we have taken a factor of safety in the passive resistance. We have only taken 50% of the passive resistance. However, we take another factor of safety in the penetration depths. This is my d design, or d, which I got from this equation, 9.38, but we usually increase it by 20 to 40%. So 1.2 times my d is 11.26 meters, and I will take it 11.3 meter. So here you have a sheet pile which has a free length of 5 meters and a penetration depth of 11.3 meters. So you see here the penetration depth exceeds twice your free length, or twice your excavation depth, and that's because the statical system here is cantilever retaining wall. In cantilever sheet piles you will get a high penetration depth because that's where you get your resistance, that's where you get your stability. And of course, if you have a weaker soil or a higher life load, you will get a higher penetration depth. On the other hand side, if you have a stronger soil with a higher friction angle, or a lower value of life load, your penetration depth will be lower. So the penetration depth, it depends on many factors here. It depends on how much is your excavation, the soil properties you have, the groundwater table level, the life load, and the statical system of your sheet pile. All of these factors control how much the penetration depth will be. This concludes our first video on the cantilever sheet pile. I hope it's useful. If you have any concerns or questions, you can email me at any time. In the second video, we will talk about the anchored sheet pile So thank you for your attention and see you in the next video.